Okay, welcome to Office Hours and today's review session. And we will largely be covering material from lectures 3 and 4 today, as well as the format of lecture quiz number 1 with some example questions. I will also go over what sort of questions you might come across that would be related to the articles in the video clip that I assigned last week, the climate articles, and the clip of Frozen Planet. And I'll touch a little bit on Lab 2 and what connections might exist between the lecture material from last week and Lab 2. So the Lab 2 is going to be due on Friday, April 16th, this coming Friday, and then Lecture Quiz 1 is going to be due 2 days after that on Sunday, April 18th. And to give you a heads up for some upcoming work, the first reading assignment, the popular news article write-up, is due a week after Lecture Quiz 1. It's due on Sunday, April 25th. And for that assignment, you pick a non-academic article about Antarctica, like a news article. And much of this review session is going to be about the climate lectures, as well as the format of quiz number 1. But I will also talk a little bit about Lab 2. So could I request that whoever that is coming from could mute, because there's some static that's disrupting the presentation. I apologize. So some of the material that we covered in lectures 3 and 4 is going to be quite useful for Lab 2 on oceanography and circulation, especially the material on Hadley cells, how air circulates from one latitude to the next, both high up in the atmosphere and at Earth's surface, as well as the Coriolis effect and how that causes deflection of those air masses. And I will talk again about the Coriolis effect in this session. There's also useful information about surface currents, upwelling and downwelling, and the formation of Antarctic bottom water in lecture 4 that you will want to review before you take the lab. The teaching assistants have also put together a helpful presentation under the folder that says Lab 2 Materials Needed. And look at those slides because they have a good review of the Coriolis effect in there, and it does a good job of identifying what specific material is useful for the lab questions. So does anybody have questions about lab before I move on? And remember that the TAs have their sections starting tomorrow and will be available to answer questions during those.
I just had a quick question, I guess. Will material from lab, like specifically related just to lab, be on the quiz, or is it more just like stuff from lecture that's on?
That's a really good question, actually. And no, material from the labs will not be directly tested on for quizzes and exams.
Okay, awesome. Thank you.
Yep. Other questions? Okay then, so let's talk about some of the takeaways from the climate lectures, because they sort of flowed together and they delved into a lot of specifics. But this slide has what I view as the most important takeaways, especially in terms of how the modern climate of Antarctica is brought about, the factors that lead Antarctica to be as cold, dry, and windy as it is. So we learned about how solar radiation is uneven at different latitudes. It's spread out more at the poles, and that leads to the formation of atmospheric circulation cells because there ends up being an excess of energy at the equator. And even though the air circulation doesn't take the air directly from the equator to the pole, there's a series of cells that exist. Overall, it still serves the function of distributing energy towards the poles, even though the poles are still cold. The poles would be even more miserably cold if this air circulation wasn't happening and overall bringing energy to the poles, but it's still cold. And Antarctica is kept cold by a combination of the effects of Earth's tilted axis, because since Earth's axis is tilted and since it's always pointed in the same direction, it's always pointed, at least over geologic time, in the same direction. That means that for part of the year, one of the poles is going to be mostly in light and the other pole is going to be almost in complete darkness. And then during another part of the year, that situation will be reversed. What that means is that Antarctica is in complete darkness for a good chunk of the year, which makes the winters especially cold. Even outside of that, the fact that sunlight hits the poles at such a spread out angle means that even during the summer, the poles are still cold. The polar summer is still quite cold. And in terms of atmospheric circulation, you have air falling around the South Pole as well as the North Pole. And that creates a high pressure zone. And in a high pressure zone, you usually have dry air falling because the moisture in the air has been lost wherever the air in that atmospheric circulation cell was rising. The high pressure also does a lot to explain why Antarctica is so windy, because you have the katabatic winds, or the pressure winds, that result from air falling around the South Pole and then spreading out towards the coast and being made to go faster because they're heading down the domed slope of Antarctica's glaciers. And that produces intense winds, especially near the coasts where the winds start to get channeled into valleys and you get a wind tunnel effect. So we talked about the structure of the atmosphere, and probably the most important takeaways from that are that the ozone layer is in the stratosphere, the second highest layer of the atmosphere, and that stratospheric ozone plays an important role in reducing the amount of ultraviolet radiation that reaches the Earth, because too much ultraviolet radiation is really bad for living things, including us. And Antarctica is seeing depletion of ozone from a number of factors. The ozone is being depleted by chemicals in the atmosphere that have been released by humans, like chlorinated fluorocarbons and nitrous oxide compounds. Those have ended up accumulating at the poles, and during the winter, they get trapped around the South Pole by the polar vortex. And so the ozone hole gets most pronounced in the winter when the air above Antarctica is especially isolated. In terms of other bits of the atmospheric structure, what I lingered on most was that most weather, most storms and such occur in the troposphere, the layer that is immediately above the Earth's surface, and that you get the southern lights in the thermosphere, where you have solar wind reacting with the Earth's magnetic field, and that's especially visible near the poles because that's where the magnetic field is slightly weaker, and so you get more flare-ups there. And when we moved on to ocean circulation, I will have two slides that detail some points related to surface circulation and deep water circulation, or thermohaline circulation, because they largely operate as independent processes. The Antarctic circumpolar current is a surface current. It's the current that surrounds Antarctica and blocks warm air as well. I say warm air here, but it's mostly warm water. It blocks warm water from reaching the continent and providing warmth. Now, in terms of deep ocean circulation, the most important point to remember about Antarctica is that Antarctica is where, in a number of locations, Antarctic bottom water forms. Antarctic bottom water forms as a result of sea ice formation, and the sea ice formation causes the remaining water to become saltier, and it sinks to the very bottom of the ocean and then spreads out as it moves north and helps distribute oxygen as well as nutrients to the world's oceans. Antarctica is also kept cold by its ice sheets, and the ice sheets, as I've alluded to and that I'll linger on more when we get to geology, formed as a result of the Antarctic circumpolar current. The circumpolar current developed around Antarctica, and the record of the first ice sheets comes shortly after that. And the ice sheets have accelerated Antarctica's cooling because light-colored surfaces like ice reflect a lot more light than do darker-colored surfaces like rock or soil or forested land or grasslands or whatnot. And that is a lot of material. I'm actually going to have a little bit of a mini study guide on the next slide, and I will be uploading these slides to GauchoSpace immediately after this session ends. But these are some general concepts before I show you the individual terms. Now, as for the example question, it's meant to get you to think about the connection between latitude and why Antarctica is so cold, and the fact that it's going to be warmer where the sunlight is hitting Earth more directly. So, at what latitude does sunlight hit Earth least directly? A, the equator, B, 30 degrees south, C, 30 degrees north, D, 60 degrees south, E, 90 degrees south. It is going to be E, because E is the South Pole. E is as far as you can get away from the equator. And at the North and South Pole, that's where the sunlight is hitting the Earth least directly. So a good clue is that one thing you can note here is that there's a 30 degrees south and a 30 degrees north, and it's going to be about the same at both of those two, so it's not likely to be either of those. It's about the same, at least on an average year-round basis as that. And then you want to remember that larger numbers for latitudes mean you're closer to the pole. And for latitude, for how north or south you are, 90 degrees north is the North Pole, and 90 degrees south is the South Pole. And that's where you're going to have the weakest sunlight, basically. And don't worry, that's what the practice questions are for. So this is actually a lot of what's going to go on the study guide for the midterm exam. These are the key terms from lectures 3 and 4 that are pretty exhaustive in terms of specific terms that you can expect to see quiz and exam questions about. And if you find yourself struggling with any of these terms, it's a good time to ask me or your TA for help. And so the example question here is to largely test whether you know what a concept involves. So the process in which the Coriolis effect and friction cause surface water to travel in a direction deflected 90 degrees from the wind is known as A, thermohaline circulation, B, convection, C, upwelling, D, Ekman transport, or E, Milankovitch cycles. And notice surface water. And yes, the answer is D. Thermohaline circulation is deep water circulation. Convection is a general term for water or air or magma circulating around and doesn't really have to do with this. Upwelling is not what's happening here. And then Milankovitch cycles have to do with Earth's orbit around the sun. So yes, the answer is indeed Ekman transport. And as for a quick review of the Coriolis effect, I find that what you need to remember is that the equator spins fastest and the North Pole and the South Pole spin slowest. And an air mass or an airplane or a water mass or a projectile that is traveling fast enough, either to the north or to the south, will experience the Coriolis effect as it travels from one latitude to the next, because different latitudes spin at different rates, but the airplane or the air mass will, as a result of inertia, think that is, or act as if it's still spinning at the rate of whatever latitude it started at. So if an airplane pilot, for example, doesn't correlate for the Coriolis effect, then they will be deflected relative to their original direction. Now, if you are in the northern hemisphere, this deflection is going to always happen to the right of whatever their intended direction was. And it is very important to not confuse left and right, which are terms that have to be defined by the viewpoint. So, for example, this is why people always have to say your left or my right to clarify what they mean by left and right. Without that clarification, left and right don't really mean anything. So in the example above in this diagram, if you are traveling north from the equator to the North Pole and you don't take the Coriolis effect into account, you will end up too far east. The red lines are what people, or what the pilot thinks their route should be, or what their route would be if there were no rotation from the Earth. The black lines represent where they actually end up if they don't take the Coriolis effect into account and if there's not other factors like wind blowing them in a different direction. So what's happening is that you are spinning faster at the equator than you would be if you were standing at this latitude. When you're flying up in the air, you are still spinning at the rate you were at the point where you left from, and you are essentially spinning too fast. You're ending up being dragged in the direction of Earth's rotation and ending up to the east and to the right of your original direction. And in the other northern hemisphere example, you are still the deflection is still to the right of the original direction. You have to notice which way the arrows are pointing, and I suppose I could have made the red arrows a bit bigger. Now, if you are flying from the North Pole to the equator, we are still in the northern hemisphere, your spinning velocity is slower than if you're starting at the pole, you are spinning pretty slowly to begin with. as you get closer to the equator, you are still spinning slowly, but the Earth underneath you is spinning faster and faster as you're getting closer and closer to the equator. And you will end up to the west, since the Earth underneath you is spinning faster than you expect. And notice that the red was what you thought you were doing. This is where you actually end up. And from the viewpoint of this vector, you are ending up towards the right of that, if you were looking towards the equator, essentially. And in the southern hemisphere, the deflection happens to the left, because whether you're in the northern or the southern hemisphere, Earth is rotating the same way. Earth is rotating from west to east. So if you're heading towards the South Pole from the equator, you are still going to be dragged east if you don't take the Coriolis effect into account, because again, when you're at the equator, you're going pretty fast. And at the equator, when you take off, you still continue to spin at the velocity that you would be if you were still at the equator. But the ground underneath you is spinning slower and slower as you head towards the South Pole. So you end up going too far east again. And this is now to the left of your intended direction, the intended direction being the red arrow here. And again, if you have the same situation, if you have the situation happening when you're going from the South Pole to the equator, you end up going too slowly, and you again end up being deflected to the west, and that is to the left of your intended direction. So, any questions about the Coriolis effect? It is something that takes practice to get an intuitive sense of, but it helps a lot to consider the viewpoint. And that's often why I use an airplane pilot as an example, because it's relatively easy to imagine yourself being in the cockpit of a plane, and that puts you in the viewpoint of deflection to the left of what's supposed to be your intended path, or deflection to the right of what's supposed to be your intended path. And in the lab, you'll also work through the Coriolis effect a bit. You'll do some exercises that walk you through developing a better understanding of why it causes air masses to be moved.
Would you say then it's probably good to work on and/or finish the lab before taking the quiz?
I believe it will help. Now, I mentioned before that the lab is not being directly tested on, but it might help improve your understanding of some of the material covered on the quiz.
Okay, thank you.
How many questions are on the quiz?
I will get to that, but 12 total, 10 multiple choice, two short answer.
Okay.
Going to surface circulation in particular, we talked about Ekman transport, which was the subject of one of the example questions before, as well as how the Coriolis effect creates gyres in which water essentially just moves in a circle endlessly and traps water in it, and how surface currents can bring warmth to continents, or in the case of the cold, fast Antarctic circumpolar current, block those warm currents from reaching continents. And we also talked about fronts, how you have places, how water masses with really different properties don't mix easily. They don't mix along a smooth gradient. There's a small narrow zone of mixing, and you'll often be able to, if you're measuring temperature on one side of a front versus the other, you'll be able to detect a sudden temperature drop or possibly a sudden change in salinity. So the example question is meant to remind you of the definition of a front. True or false, water masses of different density mix easily and along a smooth gradient, and the answer is false. And the Antarctic convergence is a really good example of a front, and a really good example of how on one side of a front to the other, you have often distinct temperature drops. Heading north from the Antarctic convergence towards Antarctica to the south, you will notice a temperature drop of several degrees Celsius because the warm equatorial waters are not mixing well with the cold polar waters. And the Antarctic convergence is a good feature to remember because it actually defines Antarctica in many ways better than the Antarctic Circle does. The Antarctic convergence actually surrounds the entire continent and pretty much all of the subantarctic islands. This is not the Antarctic Circle, actually. The Antarctic Circle is another line of latitude that defines the points below which everything experiences at least one 24-hour period of darkness. And if you look at a map of the Antarctic Circle, part of the peninsula and some bits of East Antarctica are actually north of it. So there are a few parts of Antarctica that don't experience 24-hour daylight or 24-hour darkness. And the Antarctic convergence is actually a big reason why the circumpolar current and the convergence are a big reason why the Antarctic is colder than the Arctic, because there is not an equivalent feature existing in the Arctic. So any questions about surface ocean circulation that you came with? As for deep ocean circulation, here is a summary of what makes Antarctic bottom water, and that's the main takeaway from deep ocean circulation that I wanted to linger on in lecture. And so in the example question is here to remind you of the sites at which bottom water forms, and those are known as polynyas. So when a polynya, or when a gap in the ice forms, what happens? A, sea ice melts. B, exposed seawater freezes to form sea ice. C, Ekman transport carries seawater away. D, the water becomes less salty. Or E, the water is deflected to the right. The answer in this case is B. It doesn't have anything to, so when a polynaya has to do with Antarctic bottom water formation, you either get them at the coast, where you have the pressure winds pushing ice away from the coast, and that exposes seawater that then freezes. And so the answer is B, exposed seawater freezes to form sea ice. It can also happen out, you also get open ocean polynyas where you have two water masses separating, causing upwelling of relatively warm ocean water that then freezes when it's exposed at the surface. So when a polynaya forms, you don't have sea ice melting. You have more sea ice forming, actually. And Ekman transport has to do with surface water moving around, not so much with a gap in the ice and deep Antarctic bottom water forming as a result of that. It's not D, because actually the water ends up becoming more salty, because when sea ice forms, the remaining water underneath has more salt in it per unit area. And then answer E is about, again, it's another way to talk about Ekman transport and the Coriolis effect, and that doesn't have a whole lot to do with Antarctic bottom water formation. And I'm glad to hear you get that. And Antarctic bottom water forms because Antarctica is one of the few places it's a place where the pycnocline, or the density separation between the surface and deep ocean, is not very pronounced. And what can be a little bit confusing is thinking about what's going on with the ocean as a whole versus individual masses of water, like small localized areas of water, essentially. In polar regions, the weak sunlight heats the surface not as well, and that causes less evaporation. And so the surface is about as cold as the underlying layers. It's also about as fresh as the underlying layers because there is less evaporation. And at the equator, for example, evaporation removes water from the ocean and puts it in the atmosphere, and the salt doesn't go with that. And so in general, Skylar, going to your question, when salt is in the ocean water, remember, can be either a liquid, a solid, or a gas. Water can evaporate and turn into water vapor. It can also freeze and turn into ice. The salt does not go with the ice, nor does it go with the water vapor. So what happens when sea ice forms is that you start out with a set amount of water, and then that entire amount of water is not going to freeze. You're not going to freeze the entire ocean. You're not going to suddenly freeze even the water in a single sea or bay around Antarctica. The surface water is going to freeze. The salt that was in that surface water is not going to go in the ice. If you were to take that ice away and put it in a glass, it would produce fresh water because there's no salt in the ice. The salt gets left in what little water is left behind. what you want to remember is that salt stays dissolved in liquid water. It doesn't go into ice, and it doesn't go into water vapor. And you have less liquid water left over when sea ice forms, but then you have all of the salt that was originally in both the liquid water that's left, as well as the water that used to be liquid water, but is now making up sea ice. And so that makes it more dense, and it then sinks to the bottom of the ocean. And it can do so because the water surrounding it, both the surface water and the deep water, is about the same temperature and salinity. There's not a lot of stratification, so it just sinks below everything and then spreads out as it moves away from Antarctica. As it moves away from Antarctica, it doesn't have as easy of a time rising up again because the pycnocline, the density separation between the surface and ocean water, becomes a little more stratified again. Does that help a little bit? Okay. Glad to hear that. And this is something that happens in the Arctic also. It happens in the North Atlantic Ocean primarily. And both Antarctic bottom water and North Atlantic deep water, which is the Arctic equivalent of this, play an important role in circulating ocean water, including dissolved oxygen and nutrients around throughout the world's oceans. Something we'll talk about when we get to ecology is that especially in the winter, there's a lot of nutrients in the water because in the winter there is very little biological activity in Antarctica. And so nutrients just sort of accumulate and get taken down by Antarctic bottom water and spread throughout the rest of the world. So any questions about this before I move on? So I will get now directly to the lecture quiz overview. So it's going to be a total of 10 multiple choice or true or false questions that will be automatically graded, and each of those will be 1 point. And then there will be 2 short answer questions that you do not need to write an essay for. You need to write 2, maybe 3 sentences if you really feel like you have a lot to say about it. But each one is only 2.5 points, and it's meant to be a short answer, not a big essay question. And your TAs will grade those once the quizzes are submitted. It is set to give you 30 minutes. You get a single attempt, and it's due Sunday, April 18th at 11:59 p.m. So don't do it too close to the deadline, just so you don't have to rush too much. And I've put a couple of possible short answer questions in here, as well as the type of example answers we're looking for these questions. And these are meant to give you a sense of how I might test you on the articles or the video clips, because I mostly use the articles and the video clips to reinforce concepts from lecture and maybe make, especially with the video clips, maybe give more of a visual aid for them. So, for example, I have a question about the article that was definitely the more dense of the two, but I mostly reference the fact that, but the question is more about what happened to Antarctica's climate when the ACC opened up. And you don't necessarily need to know when precisely that happened. I've alluded to it, but it's something I'll talk about more with the Earth history of Antarctica. But it's important because the ACC blocks warm currents from reaching Antarctica, and that's about when Antarctica's ice sheets formed. The other example question alludes to the Lake Vostok article and talks about how, in general, Lake Vostok is one of the coldest places on Earth. And the answer has to do with the heat capacity of ocean water and the continental effect, not directly from memorizing something from the article, but from a concept we've talked about in class a fair bit. And again, this is about the length that you would want to answer for one of these questions. Answer the question, get your point across, focus on what key terms there are from class, and then get it written down, and move it on, and don't obsess over it for too long. And I will also say I haven't talked much about I haven't reviewed geography much in this session because there is a separate review session that happened last week for that. The material covered on the quiz is going to be lectures 2 through 4, as well as the climate articles from last week and the video clip of Frozen Planet. But again, it's more heavily based on the lecture material. The articles and the clip are kind of there to reinforce. Lectures 5 and 6, which I am releasing this week, are not on the quiz at all. So don't worry about that. I haven't released lecture 5 yet, and that is not on this quiz. So I hope I've addressed most of what there is to know about the quiz, but does anyone have questions? And the quiz is meant to be kind of a check-in before the midterm exam, because we're actually about a quarter of the way through the quarter already, which is kind of hard to believe. But there aren't going to be any short answer questions on the midterm. The multiple choice questions, though, should give you a pretty good idea of what's going to be of what type of questions to expect on the midterm. All right, well, thank you all for coming by, and I'll be around for office hours for a little bit. And if you come up with more questions you didn't have during this, or if you're watching this as a recording and you have questions, feel free to email me or come to office hours on Wednesday also. But I am going to turn the recording off, and I will be around to answer questions in the meantime. And thank you all for coming.